Okay, welcome back. We're going to go to experiment number 2-1, lamps in series. So kind of flip to that page in your packet, and we're going to record some things. What we need is 3 lamp sockets here that we do leads to. With the lamps in it, we have a DC power source. And again, I'm going to set that up real quick. It says turn it on. And we want to get down to about 6 volts, which is on the low end for this thing. So I got that at 6 volts and our 3 lamps, and then we need some leads. So it says connect the circuit in figure 1 with a switch closed. Note the brilliancy of the lamp. So we're in series. So we're just going to take the power to the lamp. Let's get these 2 out of the way. And return the power to the power source. And give it some power. And notice the brilliancy of the lamp. Okay, nothing to write down yet. So I'm going to turn the power off. Okay, then it says put a second lamp in series. So we're going to jump from here to here, and from here to the lamp, and then the lamp back to the power source. And we're going to give it the same amount of power. This is series. Remember, the voltage is going to vary and the amperage is going to stay the same. Okay, one of my leads isn't working. Here we go. Now, I don't know if you can tell, but I can tell those lamps aren't as bright as just one lamp because they're sharing the electron flow, and there would be less electrons flowing because there's more total resistance of adding those 2 together. So I'm going to turn the power off. If you follow along through here, I got to flip my sheet over. Then it says remove the lamps from the socket and note what happens. So I'm going to turn the power back on. If I remove the bulb, they both go out. If I remove the bulb, they'll both go out. That's because the light bulb is a part of the circuit. So once you break the lines, that's kind of like that Christmas tree scenario when the bulb breaks. That's in series. I don't know if you remember when we did the duplexes. If we would wire our leads in series to series, if the first duplex went out, it would automatically not send circuit to the second duplex. So by using those pigtails, those were set up in parallel. This is series, so all electrons flow. From our past experience, if we took readings on this, the current would be constant and the voltage varies going across these 2 here. But we're just visually seeing that. Less amperage, the dimmer the light. Okay? Now, you're going to turn that off, and then we're going to add a 3rd light in series. And return it back to the power source. And give it some power. And I don't know how well this is showing on the camera. It's even dimmer yet, but the electrons are still flowing. Same scenario though, if you take a bulb out, they will disconnect. And because they are a part of the circuit, the light bulbs should be, if you're thinking through this, remember the more resistance, or the more light, the more total resistance. The more total resistance, you didn't change the power source of 6 volts. So you get less amperage flow results in less illumination of the light. So you need to kind of write that all out and explain why. The lamps are a part of the circuit, that's why they go out, and then the amps is based on the total resistance. You can put that in your own words and answer that, but since there's less amperage, because there's more total resistance, less amps, the dimmer the light. Okay, I'm going to shut that off. Okay, that concludes 2-1, which is in lamps in series. So now we're going to go to 3-1, lamps in parallel. So we need our same 3 lamp sockets. We still need a DC power source, and we've got our lamp modules here. So we've got lamps and lamp modules. We need to take these apart. Let's not getting to her here. We might be able to reuse some of this stuff. disconnect our power leads. Let's read what it says here. It says, connect the circuit shown figure 1 without lamps in the sockets. Okay, so I'm going to take lamps out of the sockets. And we're going to wire these up, excuse me, in parallel, which would be just like our resistors were. We jump the power to the power, to the power, to the power. And then we're going to return that on the opposite side of the circuit. And I need another one of these. And now we are in parallel. All the electrons can jump across. Voltage stays the same from one side to the other. It says insert a lamp into 1 and notice the brilliancy. So we got to hook this up to a power source. So we're sending electricity through the circuit. I can get that to hook. And then we're going to hook this to this one here. And then it says insert a lamp into socket 1, which is the first one. Hopefully I didn't break one of these bulbs. If I can get it to go in there. There we go. Power it up. Notice how bright that light is. Okay. If you remember right, that is brighter than what it was with the lamp in series. Now it says insert a second lamp into L2 and describe the brilliancy of that. Kind of watch that bulb while I put this one in here. I don't know if the camera shows it, but they pretty much are the same. Same luminancy, same brightness. I want you to think about why that is. And then if you go to the third one, same thing's going to happen. No matter how many bulbs you hook up here, same amount of electricity. Let's think that through. Why is that happening? Now, if we take out any of the lamps, though, the other two will stay lit. Other two stay lit. The other two stay lit. Okay, so now, oh, pop that sucker out. Let's try it again. Now, let's think this through. In parallel, the voltage stays constant. Okay, so you're sending the same amount of voltage through each light. If you're sending the same amount of voltage through each light, they have all the electrons they need to illuminate that bulb as bright as it's going to get. And so you would be running your amperage through each light bulb. Get the same flow, voltage is constant, current can stay the same illumination. If you break the light bulb here, the bulb is not a part of the circuit, so the electrons can keep flowing without the light bulb to complete the circuit like they were in the series. So considerable difference between a series and a parallel. Let's kind of put this in a ag section. Let's say I have 3 electric motors running seed meters on my planter. If I wired those in parallel, all 3 of those motors would run at different speeds because the voltage would drop at each one. If I want those motors to run constantly the same speed, I need to wire them in parallel so the voltage stays constant. Does that kind of make sense? So that's our 2-1 and our 2-2. Answer the questions accordingly. I'm just going to keep recording and going on. Now I want to talk a little bit about batteries. Batteries are a power source. While I'm talking, I'm going to start disconnecting things here. I'm just going to get these out of the way. Batteries are sources of electrical power. I've got different size batteries here. They are creating the voltage or the electrical potential from one terminal to the other with a chemical reaction going on in between those two. These particular batteries here, this here is a AAA and it says, or excuse me, a AA. It's 1.5 volts. This is a C, it's 1.5 volts. This is a D, which is 1.5 volts. Those are all going to create the same amount of electrical potential. Let me get that shut off. Same amount of electrical potential. They're just a bigger source. This one will only holds a less total electrons stored in there than this one, and vice versa. So the bigger the battery, you don't get more voltage. You just get more total electrons that are available to flow so they can last longer. They won't make the lights any brighter. So if you wanted to check the voltage out, again, we do our multi-tester. We've got to get our common on the volt side. We got to turn our dial to the volts. And we've got to put it on DC. Then we can take our two leads. If our voltmeter is going to read this larger D, if I connect it to the ends. Oh, come on, work today for me. Voltage, common, what's going on here? Yeah, like I said, my fuse is, so this would read somewhere about a 1.4-ish. And we get another reading here. That would be about a 1.4 to a 1.5, and this would be the same scenario. Let me double check and see what I may have something wrong here. Maybe I can get this sucker to work. Maybe it's a difference of getting the leads in there. Oh, might help if I put it on volts. Okay, let's try this again. Make sure we're on DC again. Here's our D size. Might help if I use the leads. Okay, got too much stuff here. So we put a lead on a lead. 1.48. That's almost a fully charged battery. Put these two together. And we get about the same reading. 1.46. Discharge a little more. This AA. Again, all three of these are roughly 1.5 volts. Now, I've got 4 different types of batteries or different brands, but those are all 9-volt batteries. Size has nothing to do with it. They're little square shapes. If I connect those two, this one is only going to give me about 7.6, so that's discharged quite a bit. It's only about 7 out of 9, which is a fairly low percent, under 90%. That's 7.2. This one's almost half gone. It's 4.6. And this one's about a 7.2. But all of those would be 9-volt batteries. The Battery Institution decided, well, if we want to make batteries to have the same voltage, they'll look the same. Leads are opposite ends. They're that shape. The 9-volt batteries are this shape. If you take your car battery, it's going to be considerably bigger than all of these. It's only 12 volts. So the size of the battery has nothing to do with the, but the amount of voltage will determine how much electrons it can push through a resistor or turn a light on. Now, the problem with the battery, I don't know if you can see the diagram here, part of the current flows through the battery, so it's fighting itself for the flow of electrons because you have internal loss. But that's basically what a battery is. So let's flip this over and go on to experiment number 1-2. We're using dry cells in series. So we're going to take some holders here. These little holders here are designed to hold batteries. And we need 2 of those, and we need 3 C's. So we'll get rid of these guys. So we have 2 battery holders and we have 3 batteries. And then our multi-tester, we've got that on volts. We've got it on DC, so we're ready to go with our leads. It says connect the voltmeter across the terminals of 1 dry cell. We've already done that. That was about a 1.4, 1.46 for each one of those. And now it says connect 2 cells in series. Now series is basically like that. So you got a positive, negative, positive, negative. So when you put it in one of these battery holders, you point the positive and you flip it and put the negative at the other direction. And then if I take one of my leads, steal this from my light. Okay. If I take one of my leads, so the idea here is putting it end to end. If I connect this here, that's pretty much the same as putting them end to end. And then I can take a reading from the top to the bottom. I had roughly 1.46 with one battery. Now this is in series. If I connect those 2 in series, I double it. So the 1.46 goes to about a 2.8. Actually, it's a little more of a drop there. If you can see there, this one is dropped down to about a 2.4. It goes 2.8 every once in a while. So when you put the batteries in series, it's just like making a bigger battery. You haven't changed. You start adding the voltage up. This battery is creating 1.5 volt in series. You add the next 1.5 volts and you get roughly 3 volts. Now, if I want to add a third battery, which is what it's asking us to do, I need another holder, okay? And what we're going to imitate is doing this. That is in series. So if I wanted to do that reading, I could lay it on the table, but we're going to set it up so we go from our positive, jumps to the negative, goes to the positive. Okay, and then I want to take this negative make sure we're doing this right. Okay, we're going to do a positive one in, negative going to the positive. And then we want a negative going to another positive. So now the beginning and the end of this circuit, I don't know if it was all in the picture there. So we've connected this end to this end, and then this end to this end. It was like stacking all 3 of those up. So if I want to check the total flow, then I'm going to go from this terminal to this terminal. Oh, wrong lead. To this terminal, 1.5 plus 1.5 plus 1.5 would be what? 4.5. We're just a little under there, 4.3, because these weren't quite 1.5s. So in series, what you need to remember, the voltage starts compounding and you add those up when you put batteries in series. So ag related here, if you have 2 batteries on your tractor or your piece of farm machinery, if it's wired in series and each battery is 12 volts, you now have a 24 volt battery. Very important that you realize that so you don't fry other things within your circuitry. If you had a third battery in series, if they're 12 volts, you would have a 36 volt system. We're playing with 1.5, so that would be your in series. So if you recorded your data, I probably should have referred that to you though. You flip your sheet over. 1 battery is roughly 1.5. 2 batteries is 3. 3 batteries is 4.5. If I added a 4th one, it would be about 6 volts. So the summary here is total voltage is the sum of all the batteries if they're in series. Okay, let's flip this over. We're going to go dry cells in parallel. 1.3 it says put the 3 cells into the 3 in the cell holders. Okay, now I've got those in there, but they're going to be tough to wire up that way. So what works best if you want to do parallels, get them all facing the same way in the holders. Excuse me. So I got positive, positive, positive. I connect this one to this one. I have now run my circuit positive down the negatives, and then run this negative. Let me get another clip-on one. Back to this one. Okay. Now we have, get that to stay there. In series, the only thing you're going to do is they're in parallel, so the voltage stays constant here. So if I would just take one battery, I would have your 1.4. If I do the 2 batteries, I still have 1.4. If I do the 3 batteries, I still have the 1.4 or 5-ish range. So regardless, I can crisscross them going across this way. I'm going to get 1.4. Excuse me, did that wrong. Get that there. Get that on that. So you got your 1.4s, 1.4s, 1.4s. Going from one end to the other end. This should be the same. So in parallel, let's see what the questions now says. Connect the 2 cells in parallel, positive terminal of the one to the positive terminal of the other, then connect the voltmeter across the 2. Okay, sorry about that. I've connected all 3. So if you connect these 2 here, let's do that a little different. And you connect these 2 here. Then you've got parallel across there, and you would get your 1.5s and your 1.5s. It doesn't make any difference. And then if you want to put then you go to the 3rd battery. I got ahead of it. So when we get done here, and then we're going to do a 3rd battery. Should have read my sheet first. I'm getting in a hurry. Now we have all 3 in parallel, and we're still going to get our 1.4s, 5s, and a 1.45s, and our 1.45s, and then our 1.45s, because we are in parallel. All the positives this side, all the negatives at this side. So we just keep adding more and more batteries. We don't increase the voltage. We just get a bigger battery if we put a 4th battery in there, which is beyond the experiment. Okay. We do a 4th battery here, and we put that to the circuit. Clip, and put another one here. Now we have 4 batteries in parallel, but no matter where we go, we still only have 1.45, 1.45. We just got it. So if we hook something up to these 4 batteries, they will just last longer than 2 batteries. Another scenario is if you have a flashlight that takes 3 C-sized batteries, you could put 1 C in there and run a wire, and the light would still work. It would be just as bright as with 3, but with 3, the light would last longer. Okay, so the voltage wouldn't change. So if we hook this up to a light to illuminate it, hook this up to a light to illuminate it. Hopefully this will work while I'm jumping real quick here. So you can see that bulb is not very bright because we're only running about 6 volts to that. or 1.5 volts to that. In a flashlight, then, if we put 3 of them in series, we would get 3 times 1.5 times 1.5 times 1.5, and then that light bulb would actually light up. Okay? So parallel, you don't gain any more voltage, just lasts longer. Series, you gain more voltage, but then they'll burn out quicker. Okay, so make sure you got the answers to these questions here for the batteries. The total voltage is constant of the individual batteries for the parallel. So 1 is 1.5, 2 is 1.5, 3 is 1.5, unless you wanted to write the 1.46. Same scenario. No extra voltage, but longer life, actually just a bigger battery. So that concludes our experiment number 1-2 and 1-3. And we will do another video to do the middle of the packet, which is looking at whether resistors are in series or parallel. And I'll try to do that here in a minute. So I'm going to shut down, and that concludes this part of the experiment.